Hello dear student, greetings for the day. Welcome to Time classes. This session is on a very interesting topic, which is law of conservation of energy, which comes in the chapter Work, Energy and Power. From smaller classes onwards, we are studying various conservation laws like law of conservation of momentum, law of conservation of mass, law of conservation of charge, law of conservation of energy and so on. Among these conservation laws, law of conservation of energy finds its application in various visible real-life situations. And so, in competitive examinations, you can expect questions where you have to apply the concept of energy conservation or energy conversion for solving. So, in this session, we will be discussing about energy conversion and certain problems which are frequently asked from this topic. So, we will see how to apply the conservation principle for solving such numericals. Are you ready for starting the session? Alright, we can start. So, what is law of conservation of energy? Hope you are familiar with the statement. Energy can neither be created nor be destroyed. We can only convert energy from one form to another. So, here we have to focus on this phrase, form of energy. We are converting energy from one form to another. So, which are the different forms of energy? We have heard about light energy, sound energy, heat energy, then mechanical energy, that means kinetic energy and potential energy, right? So, the problems which comes from this topic will be mainly focusing on kinetic energy and potential energy. Okay, which are the two forms of mechanical energy. Okay, so we are going to see kinetic energy and potential energy. Alright, so hope you know what is kinetic energy. It is the energy possessed by a body in motion. Okay, so if you are considering a body of mass m which is moving with a speed v, then the kinetic energy possessed by that body is given by the equation half mv square. Hope it is very familiar to you. Okay, so kinetic energy possessed by a body is depending on what all factors? The mass of the body as well as the speed with which the body is moving. Similarly, talking about potential energy, we have two different kinds of potential energy, which is called gravitational potential energy and elastic potential energy. So, what do you mean by gravitational potential energy? So, if you are considering a body of mass m which is at a certain height h above the reference level or ground, then the gravitational potential energy possessed by this body is given by the equation mgh, right? M is the mass of the body and h is the height of the body above the ground, and g is the acceleration due to gravity. Okay. So, hope now you are clear with the concept of gravitational potential energy. Now, let's move on to elastic potential energy. So, what is elastic potential energy? Consider an elastic material like a spring. Okay, we are considering a spring. And now, I am applying a force on the spring in order to elongate it or in order to compress it. Okay, so actually I am doing a work there for elongating or compressing the spring. That work done will be stored in the spring in the form of certain energy which is called elastic potential energy. Okay, so work done in elongating or compressing a spring will be stored in the spring in the form of elastic potential energy. Okay, and suppose if you are considering that k is the spring constant of the spring and x is the elongation or compression given to the spring, then the expression for elastic potential energy can be given by the equation half kx square. Okay, k is the spring constant and x is the elongation or compression given to the spring. Okay, for solving the problems related to the concept of energy conservation, you have to keep these equations in mind: expression for kinetic energy, expression for gravitational potential energy and expression for elastic potential energy. Okay, Hope the concept is clear. Now we have to discuss some problems which has been frequently asked in the competitive examinations, where you can apply this concept of energy conversion for solving. So hope you are thorough with the concept. Now let's move on to problems. So let's discuss the first question. Read the question. A light spring of spring constant K is kept vertical on a horizontal floor with one end firmly fixed to the floor. When a small particle of mass m is placed on the spring, compression of spring is negligible. Now the spring is compressed by a distance of x unit and released. The maximum height above the natural length of the spring attained by the particle is dash. So what is the question? We are considering a light spring. Okay, that means we are ignoring the mass of the spring. We are considering a light spring, and how is it kept? It is kept vertical on a horizontal floor. So let's draw a diagram. We are considering a spring which is mounted vertically on a horizontal floor with one end firmly fixed to the floor. Okay, and we are taking K as the spring constant of this spring. Now we are placing a small particle of negligible mass. Okay, it is a very light mass. We are placing it on the spring over here. Okay, we are placing this mass m on the spring. This is a very light mass. That means no compression is taking place on the spring due to the weight of this mass. Okay, it is a very light mass. We are ignoring the mass of this body. Okay, mass of that particle. So we are giving here a compression of x unit. Alright. So what will happen there? If you release the spring, this mass will move upwards, isn't it? This mass will rise to a certain height. This will come over here when you release the spring. The question is to find the value of this h. Okay, what is the maximum height attained by the particle above the natural length of the spring? So you have to find this height h. Hope the question is clear. We are placing a very light mass on a spring which is vertically mounted on a horizontal floor, and we are applying a force on the spring in order to compress it. And please note, the compression on the spring is not produced due to the weight of that particle. Okay, so x is the compression produced in the spring. And now when you release the spring, this mass is raised to a certain height above the natural length of the spring, and we have to find the height attained by this particle. Okay, so this question can be solved by applying the principle of energy conservation. So what is the form of energy conversion taking place here? Yes, when the spring is compressed, it stores some energy which is called elastic potential energy. And now when the spring is released, the mass is rising to a certain height. That means the elastic potential energy of the spring is getting converted to gravitational potential energy of that mass, isn't it? When you are releasing the spring, the mass is raised to a certain height. Okay, that means the elastic potential energy stored in the spring is getting converted to gravitational potential energy of the mass. So now just substitute the equations. Elastic potential energy of the spring is given by the equation half kx square, and gravitational potential energy of that mass is given by the equation mgh, because the mass is raised to a height h above the natural length of the spring. So equation for GPE is mgh. Now what you have to find is the expression for h. So from here you can write h is equal to half kx square divided by mg. So this will give you the answer as kx square divided by 2mg. So the answer for this question is option A. Hope the concept is clear. Shall we move on to another type of question? Yes. So this question is somewhat similar to the previous one, but there is a slight difference. Let's see what is the difference. So here also we are considering a spring which is mounted vertically, and here we have a pan which is attached to the top of the spring, and here we are dropping a small mass m onto the spring, okay, so that the spring is getting compressed. Okay, when this mass is falling on the pan, the spring is getting compressed due to the weight of that mass. Okay, please note that point here. The spring is getting compressed because of the weight of this falling mass. Okay, so let us consider that x is the compression produced in the spring, and let us consider that h is the height from which that particle is dropped. Okay, and in this question we have two cases. Okay, so let us mark it as h1 and x1 for the first case. Okay, it is given that when the mass is dropped from a height of 10 centimeter, it produces a compression of 1 centimeter in the spring. That is the data for the first case. And what is second case? What should be the height from which the particle has to be dropped in order to produce a compression of 2 centimeter? So the value of x2 is 2 centimeter. Then what should be the value of h2? That is the question. So here also we have to apply the energy conversion principle. So tell me, what is the energy conversion taking place here? We are dropping a certain mass from a certain height, and when it is falling onto the pan which is attached to the top of the spring is getting compressed because of the weight of that falling mass. So of course the mass is initially having a certain gravitational potential energy, right? The gravitational potential energy of the mass is actually getting converted to, yes, elastic potential energy of the spring, because when the mass is falling on the spring is getting a compression. That means the gravitational potential energy stored in that mass is getting converted to elastic potential energy in the spring. Okay, now let's substitute the equations of gravitational potential energy and elastic potential energy. Of course, the equation of gravitational potential energy is mgh, but here you have to be careful because we are dropping the body from a height h1, but because of the weight of that body, the spring is getting compressed. So here we have to consider the displacement of that mass as h1 plus x1, right? Clear? Yes. Now what comes in the RHS is elastic potential energy of the spring, which is given by half k x1 square. So that is the equation for the first case. Okay, you can mark it as equation number 1. In the same way, you can form the equation for the second case also, which will be mg into h2 plus x2 is equal to half k x2 square. Let it be equation number 2. Now you have to solve these two equations to find the value of h2. That's very simple. Okay, you can divide equation 1 and equation 2. Just do equation 1 divided by equation 2. What will happen? mg will get cancelled. Half k will get cancelled. Now we can substitute all the given data in the expression. So what is h1? h1 is 10, x1 is 1, and h2 is what you have to find out. Value of x2 is given as 2 centimeter. In the RHS, you will have x1 square by x2 square, right? That is 1 square by 2 square, which is 1 by 4. Now just cross multiply. 10 plus 1, 11. 11 into 4 is 44. So you will get h2 plus 2 is equal to 44. So h2 will be equal to 44 minus 2. So your final answer is 42 centimeter, which is there in option A. Okay. So hope you understood what is the difference between this question and the previous one. Clear? Shall we see another type of question? Read the next question. A stone is thrown vertically down with a velocity 20 meter per second from 10 meter height to a cement floor. If 20% of energy is lost on the floor, then the stone will rebound at a height. See, in this question, it is given that a stone, the mass of that stone is not given, so let us take it as m. Okay, the stone is thrown vertically down from a certain height. Okay, so let us consider that height as h, and the value of h is given in the question as 10 meter, right? Yes, and please note this point here. The stone is not dropped from rest, it is thrown vertically downwards with a certain initial velocity, and that initial velocity is given as 20 meter per second. Let us take it as u. Okay, and now it is given that when the stone hits the floor, it loses 20% of its energy. Okay, and with the remaining energy, it is rising up, it is rebounding and reaching a certain height. Let it be h dash, and this is what you have to find out. Hope the question is clear. So here also we have to apply energy conservation principle. Okay, so we can consider this point as A and this ground point as B. Okay, so first of all, let us take what is happening at point A. Yes, at point A, the stone is at a certain height above the ground, so definitely it is having gravitational potential energy, and also it is not dropped from rest, it is thrown with a vertical velocity, right? Yes, so it is having kinetic energy as well. So at point A, the stone is possessing both gravitational potential energy and kinetic energy. So the total energy of the stone at point A will be the sum of kinetic energy as well as potential energy at point A. So kinetic energy is given by half mu square and potential energy is given by mgh. Now we can substitute all the known values in this equation. We don't have the value of m, but the value of u is given as 20. So we can substitute u is equal to 20, and we can substitute the value of g as 10 and value of h is also given as 10 meter, right? So we will get here what 200 m plus 100 m, that means 300 m joule is the total energy possessed by the stone when it is at point A. Now read the remaining part of the question. When the stone is falling onto the floor, it loses 20% of this energy. Okay, so what is the loss in energy taking place when it is hitting the floor? 20% of 300 m. Okay, so 20 by 100 of 300 m. So this will give you 60 m joule. This is the energy lost. Now what is the remaining energy at point B? Yes, it is 300 m minus 60 m, that is 240 m joule, isn't it? Now with this energy, the stone is again rebounding to a certain height h dash. Okay, so how will you write the energy conservation equation? Now it is having an energy which is 240 m, and when it rises to a height h dash, this 240 m is getting converted to what? The gravitational potential energy at the point h dash, which is given by mgh dash. Okay, so from here you can easily find out the value of h dash, that is 240 divided by g. The value of g is 10, and so the answer for this question is 24 centimeter, which is option A. Yes, read the next question. The bob of a simple pendulum of mass m is released from a horizontal position A and reaches a point B so that it makes an angle 60 degree with the vertical. Then the gain in kinetic energy at B is dash. Take L as the length of the pendulum. So this is a very important kind of question. See, we are considering the bob of a simple pendulum. Okay, so we are considering a simple pendulum which is having a bob of mass m. Initially it is released from a horizontal position A. So this is the initial position of the pendulum. Okay, this is the initial position which is denoted by A. It is a horizontal position, and now when it is released from point A, it is falling downwards, and here we are considering an intermediate position which is making an angle 60 degree with the vertical. So let us consider this intermediate position as B. Okay, so when the pendulum bob reaches point B, the rod of the pendulum is making an angle 60 degree with the vertical. So this is the case mentioned in the question. So what you have to find here is how much is the kinetic energy gained when the pendulum bob reaches point B. Okay. So here, when the pendulum bob is at point A, it has got only potential energy, right? There is no kinetic energy because it is released from rest. So initial velocity is 0. So kinetic energy is also initially 0. Okay. And what about the potential energy at point A? That is given by the equation mgh. So here in place of h, you have to substitute this distance, right? What is that distance? That is actually the length of the pendulum rod, isn't it? So here the potential energy of the pendulum bob when it is at point A can be given by mgl. Clear? Now let us see what is happening when it reaches point B. When it reaches point B, the kinetic energy goes on increasing and potential energy goes on decreasing. Okay? And according to law of conservation of energy, we can say that the gain in kinetic energy will be exactly equal to the loss in potential energy. Okay, so we are starting from that statement. Gain in kinetic energy will be equal to the loss in potential energy. If you consider the motion of the pendulum bob from point A to point B, the kinetic energy is increasing and potential energy is decreasing. That is clear. And according to law of conservation, we can say that the loss in potential energy will be exactly equal to the gain in kinetic energy. So here the question is to find the gain in kinetic energy upon reaching point B. Okay, so that will be equal to the loss in potential energy. Loss in potential energy means what? Potential energy of the body at point A minus potential energy of the body at point B. Okay, now we have to give substitutions. For potential energy at point A, we already got the equation as mgl. Now we have to find what is the potential energy at point B. See, point B is at a height of say x, okay, from the reference level. So we have to find this x. How will you find x? See the figure. This angle is 60 degree, right? And see this? This is L. So how much will be this particular distance? This will be definitely L cos 60, isn't it? So what about this x? Of course, this x will be equal to the total length L minus this length L cos 60, isn't it? So here, for potential energy at point B, we can substitute as mgx, and in the next step, you can give the substitution for x as what? Yes, L minus L cos 60. Clear? So just open the bracket. You will get mgl minus mgl plus mgl cos 60. Okay. So plus mgl and minus mgl will get cancelled, and you will get mgl into cos 60. Cos 60 is 1 by 2. So the final answer for this question is half mgl, which is option A. So I hope the questions discussed in this session is clear to you. This is a very important topic from competitive exam point of view. So hope you have understood how to apply the concept of energy conservation and energy conversion, particularly regarding kinetic energy, gravitational potential energy and elastic potential energy for solving application level questions. Hope you have enjoyed this session. Thanks for watching. Have a nice day. Thank you.